let's look at another example of finding the inverse of a matrix. So let's find the inverse of this matrix A. So we know we need to take our matrix and augment with the identity matrix. So 1, 0, 0, 0, 1, 0, 0, 0, 1, and then just start row reducing. So we're going to do row 2 minus 2 times row 1, and we're going to do row 3 minus 2 times row 1. And I guess while we're at it, we might as well multiply row 1 by minus 1. So let's do the second and third row first. So minus 2 minus negative 2 is 0, minus 3 plus 4 is 1, and then 1 plus 0 is minus 1. Okay, and then in our augmented matrix part, we get, let's see, 0 minus 2 times minus 1, so minus 2, and then 1, 0. And then third row, so third row minus 2 times first row, so 0, 0, 0, and then minus 2, 0, 1, and then first row is, we're flipping the sign on it, so it's 1, 2, 0, minus 1, 0, 0. Okay. And, well, wait a second. The next thing that we should do is use this one here to eliminate anything below it, but there is nothing below it. And so then after that, we would use whatever is here in the lower right to eliminate stuff above, but we have a 0 here in the lower right. There are only 2 pivot columns here. And remember, our goal when we're looking for an inverse, our goal is to row reduce the stuff on the left to the identity matrix. But the identity matrix has rank 3. What we have here has rank 2. So we can't row reduce this to the identity matrix. This isn't going to happen. And what this is telling us is that the inverse doesn't exist. So you can't accidentally stumble onto an inverse if one doesn't exist, because when you do this row reduction, if there is no inverse, it will be impossible to row reduce to the identity. So that's a pretty clear sign that there's no inverse. One warning though, if you make any sort of arithmetic mistake when you're doing a row reduction, so if there should be no inverse and you make any sort of arithmetic mistake, you will probably make it appear to have an inverse. So you have to be extremely careful when you're doing row reduction, because any arithmetic mistake could change the answer from no inverse exists to here's an inverse. So be really careful. All right, let's look at another example of finding an inverse. And this one, this one's 4 by 5. I'm sorry, 4 by 4. So that, what we should do to find this inverse is take this giant matrix, 5, 4, 0, 3, I don't even want to write it all down, it's so big, 4, 3, 3, 4, 3, 0, 3. Augment this with the 4 by 4 identity, like this, where every entry that I haven't written down is 0. And then row reduce the whole thing. And I don't know about you, but that sounds like a giant pain. I mean, I know intellectually how to do it, but it's just a giant bookkeeping task. Well, this is still just row reduction. And if we need to do a row reduction that's too big or clumsy to do by hand, not because it's impossible, but just because it'd be too time consuming to do by hand, we can always ask a computer to do it, right? This stuff inside the brackets, it's still just a matrix, and so Sage would be perfectly happy to row reduce this for us. So let's just ask Sage to do it. I've sort of pre-staged Sage with the appropriate matrix. So notice how I did this here. When I entered this into Sage, the first row for the original matrix is here, and for the augmentation is over here. But right, as far as the matrix I'm entering into Sage, there is no distinction between the two parts of the matrix. So Sage won't really know that I'm row reducing to find an inverse. It will just happily row reduce whatever I give it. But just from the way I've typed this in, you can see that the part on the left really is the matrix we started with, and the part on the right really is the 4x4 identity. So that means when I ask Sage to give me echelon form, right, we know ahead of time, well, assuming that this matrix has an inverse, which it does, the echelon form for this left-hand part will be the identity matrix, and so the inverse matrix will show up on the right-hand part when we get echelon form. So, you know, Sage doesn't know that we're finding an inverse, but it will find the inverse for us. If I enter things correctly, which I did not. Oh, I missed a comma right here, looks like. Did I screw anything else up? No. Okay, so right here in the left-hand part, there is the 4x4 identity as expected. And so in the right-hand part, this is our inverse matrix. So 6 minus 3, 0, 4. 6 minus 3, 0, 4. Was that a minus 6? Yes, it was a minus 6. 7, 3, 0, minus 5. 7, 3, 0, minus 5. And then 18, 7, 1, minus 13. 18, 7, 1, minus 13. And 1, 1, 0, 0. Okay. So there is our inverse matrix. So the point of this example is, you know, in practice, if you're solving a big system of linear equations, or if you need to know an inverse matrix for some reason, you wouldn't actually do the row reduction by hand. You'd ask a computer to do it. And this is because, you know, often in applications, the matrices that you end up working with can be very, very large, and so you'd never do it by hand. You'd just ask a computer to do it. Okay, let's look at one more example. Let's solve this system of equations. Now, I know we already know how to solve systems of equations, but I want to rephrase this in terms of matrix multiplication. Remember, when we figured out matrix multiplication, we noticed that you can write any linear system like this: ax plus b, where a is a matrix that's m by n, x is a matrix that's n by 1, and b is a matrix that's m by 1. Right? But if we have an equation like this, and I asked you to solve for x, if you weren't in a linear algebra class and you thought we were talking about numbers, what you'd probably do is just get rid of the a on the left-hand side by multiplying by its inverse. And if you do that on the left, you have to do that on the right as well. And then these two things cancel, so you just get x on the left-hand side. And on the right-hand side, you get whatever a inverse times b is. But this calculation works just as well for matrices as it does for numbers, right? The only caveat here is that this product, A inverse A, is the identity matrix of size n, which is n by n. X is a matrix or a vector, it's n by 1. And so this product just gives us x. So you can see that one nice use of an inverse matrix is to solve linear equations. So let's do that here. Let's see, if we write this as a matrix equation, it's going to be minus 3, 0, 1, minus 1, 1, minus 4, 2, minus 1, no, 2, 0, minus 1, times, right, our matrix of variables, x, y, z, equals, our right-hand side is 7 minus 2, 4. Okay, so now let's find the inverse. So this is our matrix A right here. Let's find the inverse for A. So I'll be lazy and ask Sage to do it. So we only need 2 rows, not 3. And we want to augment with the 3 by 3 identity, and our rows are -3, 0, 1, -1, 1, -4, -1, 1, -4, and then 2, 0, -1, 2, 0, -1. Okay, and then hit go. All right, so it did. The left-hand part did reduce to the identity. So -1, 0, -1. -9, 1, -13. -2, 0, -3. Okay. There's our inverse matrix. And now to compute our matrix of variables, or our vector of variables, we just need to compute A inverse times the matrix of the right hand, or the vector of the right hand side, 7, -2, 4. Okay, so now we can just do this matrix product. So -7 plus 4, -7 minus 4 is -11. And then for the second row, oh boy, we got some big numbers here. So -63 and another -72 is 130. I lost track. So minus 63. 4 times 13 is 40, and another 12, so minus 52. Oh boy. So minus 115 plus, or minus another 2, so minus 117. And then finally, last row, minus 14, 0, and minus 12. So minus 26. Okay, hopefully I did the arithmetic there. But you get the idea. So if you have an inverse matrix, you can easily solve a system of equations because you just multiply the right-hand side by the inverse matrix that you found. Now, you're probably thinking, well, finding the inverse matrix is actually more work than just solving this equation, so why would I find the inverse matrix to solve this equation? Well, to be honest, you wouldn't. If this were the only equation you were solving, you would just solve this equation by row reduction. You wouldn't bother with the inverse matrix. But in applications, it's actually common to have to solve many, many equations where the matrix is always the same, but the right-hand side is always different. So you might have to solve this equation where you have some column matrix on the right-hand side, and then solve this equation where the matrix is the same, but the right-hand side is different, and then so on. You might have a million of these kinds of equations to solve. Would you want to do row reduction to solve every one of these? Well, no, that's a lot of work. Instead, you can find the inverse matrix once, right? Because we're assuming that the left-hand side matrix is the same for all of these systems of equations. Find the inverse matrix once, and then you can just do all of these matrix products. A inverse times your first right-hand side, A inverse times your second right-hand side, and so on, up to A inverse times your millionth right-hand side. You still have a lot of arithmetic to do to work out these matrix products, but that's a lot less work than solving each of these systems independently. So it's still a lot of work, but it's much, much less work than it would have been otherwise.